Hello, and welcome to the Sustainable Materials Management Webinar Series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Scott Marks, and I'm Program Manager for the Recycling Market Center. I will serve as the moderator today. Today's webinar topic is Innovative Waste Gasification Technology. Please note that the Pennsylvania Recycling Market Center, its affiliates and funders, and the National Recycling Coalition assume no liability resulting from the use of any information provided during the webinar. The webinar is only provided as an informational tool, and no discrimination is intended and no endorsement by these organizations is implied. Our presenter today is Abraham Haspel, whom I will introduce in a moment. Following the presentation, we will conduct a question and answer session. If you have a question or comment, please use the Q&A feature located in the control panel found on the bottom of your screens. You may also use the chat feature to request assistance if you are experiencing technical difficulties during the webinar. Please note that an edited version of this webinar will be made available for viewing via YouTube on the National Recycling Coalition and Pennsylvania Recycling Market Center's websites. And now I'm pleased to introduce our presenter. Dr. Abraham E. Haspel is the founder and president and CEO of Cogent Energy Systems Incorporated. He is also the president of Cogent Analysis Group, LLC, an energy and environmental consulting firm founded in 2008. Prior, Dr. Haspel spent more than 30 years as a decorated career senior executive at the U.S. Department of Energy, where, among other positions, he was Deputy Assistant Secretary and Chief Operating Officer for the Office of Energy Efficiency and Renewable Energy, successfully managing an organization with more than 500 employees and a budget of more than $1 billion, and at the U.S. Department of the Interior, where he was the Assistant Deputy Secretary. While at the Department of Energy, Dr. Haspel was also one of the lead U.S. negotiators between 1993 and 2000 at the UN Framework Convention on Climate Change, including the negotiations that led to carbon trading and the Clean Development Mechanism provisions of the Kyoto Protocol in 1997. He chaired the OECD's Clean Technology Initiative from 1998 through 2000. Dr. Haspel holds a Ph.D. in economics from the University of Pennsylvania. Dr. Haspel, the floor is yours.
Well, thank you very much, Scott. I'd like to begin by thanking the Pennsylvania Recycling Market Center for giving me the opportunity to present to you today. Let me also thank you for taking the time to listen. Next slide, please. I've organized this presentation to answer the who, what, when, where, why, and how questions I'm sure you all have, though not necessarily in that order. The disclaimer on your screens, just like Scott's, is courtesy of our lawyers and applies. So let's get started. Next slide. So why? As you're aware, in addition to billions of tons of agricultural biomass byproducts, municipal solid waste production worldwide is expected to reach almost 3.5 billion tons by 2050, according to the World Bank. This growth is seen in all geographic regions and types of waste, and it hits particularly hard in underdeveloped regions of the world. Unless the world finds new and better ways of handling this waste, landfills will overflow with catastrophic consequences. Rather than attempting to bury all that waste, many believe that the world should try to extract the resources still tied up in that material and turn waste from an expensive disposal problem into valuable commodities. Next slide, please. As a society, we're moving from a linear view of resource use that ends in disposal and pollution to a more circular one. The diagram's on the left-hand side of this slide. Yet at some point, even in the current view of the circular economy, organic materials can no longer be recycled efficiently. We believe that instead of going to the landfill, end-of-life plastics, tires, cardboard, and other materials can be recycled into their carbon, hydrogen, and oxygen components. These molecules can then be converted into fuels, chemicals, or electricity that serve as inputs to the next round of production. At the recent NAWTEC conference in early April, the director of the Office of Bioenergy Technologies at DOE called this recycling molecules. Next slide, please. However, to deliver the solution described on the last slide, a disruptive technology solution is needed. Much like the evolution from huge room-sized vacuum tube computers that struggle to complete complex tasks to today's powerful microprocessor-based laptops and tablets, the waste conversion market is ripe for disruptive technology innovation that yields smaller, more efficient, more deployable solutions to meet the needs of the broader marketplace beyond simply metropolis-scale facilities. And in so doing, we create white space opportunities, markets which are not big enough to attract these large-scale technologies. On the left of the slide here, you're seeing the 1945 ENIAC vacuum tube computer and today's Mac-top laptop. Interestingly, the 1945 vacuum tube was at the University of Pennsylvania, and that's where I got my doctorate, and that's who's sponsoring us today. So it's interesting how Pennsylvania keeps playing a role. On the right is Baltimore's Wheelabrator waste-to-energy plant, and above it is our technology. So you'll go to the next slide. Our disruptive technology is called the HelioStorm Gasifier. It processes waste at 5 to 15 times the heat of our competitors. This means that beyond just breaking down larger molecules, we actually vaporize the carbon in the waste stream. So we're able to efficiently deliver a pure synthesis gas, ideal for conversion into fuels, chemicals, or electricity in a very small, flexible package. At these temperatures, it is possible for us to process virtually any type of feedstock in our compact unit. In addition, the patented innovations in our system design limit the total input energy requirements, which greatly reduces our parasitic load. This makes us a different kind of gasification technology. As a result, we can create surplus energy, either in the form of electricity or fuels from waste feedstocks, and do so at rates that we believe yield attractive economics. Next slide, please. So who are we? We're a young company. We were founded in 2012, but really only have been actively operating since about 2015 when we secured our initial financing and began developing outside of the national lab system. The names here, you can simply look at our executive team. Our team brings decades of experience as senior executives in the public and private sector, both in the United States and in Canada. We have PhDs with science backgrounds and lots of international sales and project development experience. Next slide, please. Let me also acknowledge our engineering partner, Criari, who has been extremely important to our success thus far. Criari has been around for almost 60 years. They are one of the Navy's go-to engineering solution providers. They were intimately involved in the repair of the Hubble telescope, and they've engineered parts for the Mars rover. The upper left quadrant of this slide is their campus in Hanover, New Hampshire, which is overlaid by the names of some of their clients and partners. All of them are household names that you'll recognize. But in particular, let me point out Lockheed Martin, which is now heavily involved with the project shown in the lower left quadrant, right-hand photo, which is a core tool in the manufacture of the F-35 aircraft. Criari engineered this piece of equipment, and Idari, one of Criari's spin-offs, which is shown on the right-hand quadrant, is manufacturing it under contract to Lockheed Martin. We see a similar type of arrangement. I like to say Criari is not only world-class, but universe-class. And if they can engineer for outer space, they certainly can engineer for planet Earth. Next slide. As you can see on this slide, we have received support for our technology approach from the Navy, DOE, and 2 national labs. As you know, Small Business Innovation Research grants and DOE's small business vouchers and high impact program grants are all extremely competitive. And we take it as a very good sign that these organizations have awarded them to us and continue to fund and support us as our technology and company has developed over the last few years. And I would like to also point out that about a month ago, Cogent received the 2019 Technology Focus Award from the Federal Laboratory Consortium, which is an umbrella group comprised of all national labs, military labs, and other research facilities across the government, recognizing our success in technology transfer and partnership with the Idaho National Laboratory. And in fact, we were the only company to win one this year. So, next slide. So what is ionic gasification? What's the basis of our new technology? So to understand this, we have to dig into the science a bit more. And the temperature graph on the left really tells the story. Until now, thermal gasification relies on indirect heating of the air in a container, usually in conjunction with a superheated substrate such as molten glass, but has never reached temperatures that exceeded 2,200 degrees centigrade. Now this is important because temperature matters. The lower the temperature, the more contaminants need to be scrubbed from the resultant gas stream. This costs energy in the system as well as increases the capital expense. Once you get above 3,000 degrees, a lot of different things happen. At 3,000 degrees, water will decompose into hydrogen and oxygen. Carbon vaporizes at temperatures greater than 3,500 degrees C. And at 3,900 degrees C, even carbon dioxide dissociates. And at these temperatures, uncharged free radicals are forming. And when you get to more than 5,000 degrees C, free radicals turn into high energy ions. Our secret sauce, therefore, is the breakdown of carbon, hydrogen, and oxygen contained in waste into ions. And as these ions cool, they reform into their lowest energy states, clean hydrogen and carbon monoxide, all in one step. No additional polishing of the product stream, gas stream, is needed. So how do we use this science to create a real-world gasifier? On the next slide, I'll answer your question. Here you see a schematic of our patented stacked modular design that allows us to create a continuous plasma field that is about 9 inches in diameter by about 36 inches in height within 3 vertically stacked modules. We fill the entirety of this cylinder with super hot plasma gas reaching 10,000 degrees Celsius, which, as I've mentioned, is hot enough to fully disassociate all feedstock into a pure carbon monoxide hydrogen syngas inside this single vessel without further processing. Again, our competitors simply heat the ambient environment that fills their container, but to much lower temperatures, yielding only partially converted product gas that requires further processing or polishing before it can be used. In addition, the stacked modular design gives us another key benefit. Energy and heat from the 9-inch plasma arcs in the top module cascades to the second module, acting as a preheating element and reduces the amount of input electricity required to start and maintain the arcs in the second module. Similarly, energy cascades from the second module to the third. Combined with the fact that our system requires no additional syngas polishing outside the main conversion vessel, this has the effect of reducing the total energy input required for our system, minimizing parasitic load and maximizing our net exportable energy. All of our independently verified results have shown clean, ready-to-use syngas, which we will discuss in more detail in a few slides. Now, on the next slide, we compare gasification approaches. This comparison demonstrates the difference I alluded to on the last slide. Our system on the left utilizes a drop-through processing scheme in a cylinder filled with a plasma field with temperatures reaching 10,000 degrees C, as I said. The representative competitive design shown on the right introduces feedstock into a chamber of hot air in which plasma torches with small arcs and no synergistic cascading are used to superheat a substrate, such as molten metal or glass at the bottom, to temperatures in the 1400 to 1700 degrees C range. While the small plasma arcs in the torches also reach 10,000 degrees C. Like our longer arcs, the fact that only 1400 to 1700 degrees C are used in converting the waste accounts for the much larger parasitic load or energy losses experienced by our competitors. Since our plasma field temperatures remain as high as 10,000 degrees C, we experience very little loss and ionic gasification becomes possible. Next slide. And here's what our technology looks like in real life. It's about 6 feet tall, about 3 feet wide. It's the image on the left. We are the exclusive licensee of the underlying patents from Battelle Energy Alliance, which is the manager of the Idaho National Laboratory. These were initially filed by our Chief Technology Officer, and it underpins the HelioStorm Gasifier. During the last 2 years, however, we have continuously improved the technology and processes and have prepared new patents. One of those was issued to us in February, and we have others that are now pending. The photo on the right, the lower photo, is a top-down view of a plasma field inside the HelioStorm. It's not blue, it's actually quite white, but in order to get a photo so you could see anything, we have to use a very thick filter, and it shows these colors. The circles show where the electrodes are. They're pulled back to the side of the gasifier inner shell, and you can begin to see where the arcs, and we're trying to improve how we can best represent this, but it's such bright white you really can't see it. It's like needing a welder's torch in order mask in order to process a photo. Anyway, next slide. Another product from our SBIR project with the Navy is this footprint schematic, which shows a possible layout of a HelioStorm-based waste-to-energy system. The Navy is interested in, primarily right now, in making electricity. You'll note the Navy-specific genset configuration and a large dry scrubber, neither of which is likely to be part of a commercial installation. But this gives you an idea of a potential layout. For instance, through our high impact project grant with NREL, we've been working with NREL, Perkins, and Woodward Controls to design a modified diesel genset that will use our syngas as fuel. In addition, along with Priori, we've been working to design a properly scaled filtering scrubbing system to clean the syngas of chlorine or hydrogen that, sulfur that might be in the feedstock before we can introduce it into the genset. Still, for illustrative purposes, this particular design is valuable, and for reference, it requires a footprint of about 50 feet by 40 feet, or about 2,000 square feet, and has a height of around 10 feet. Next slide. This diagram is probably familiar to many of you. It's a pretty straightforward waste-to-energy process train schematic. This particular idealized version was developed also as part of the SBIR project. Like most systems, we'll begin with feedstock being prepared and loaded into a hopper. We believe that 1/2 inch particle size is ideal for our current unit, with moisture level contents of up to 50%, though we would prefer somewhat lower. We're currently working with Idaho National Laboratory on a second grant-funded project to further zero in on these feedstock formatting specifications. As part of the Navy SBIR project, we've been working with Priori to select front-end component providers, including off-the-shelf shredders. Further, a prototype of a delivery system from the hopper to the gasifier has been designed, and is currently operational in our Idaho Falls facility. Once in the hopper, oxygen is flushed from the environment, and the material is then fed directly into the gasifier processing module. Nitrogen acts as the carrier gas for the plasma arcs, which we currently supply from tanks, but which will come from on-site air separators, which can also produce oxygen, which can be introduced into the system for optimizing and enhancing syngas composition. All the organic material is converted into synthesis gas in the HelioStorm processor, and any inorganics simply melt and are collected in the bottom catch chamber. Hot syngas exits the gasifier and is quenched and scrubbed, as I said, to remove any sulfur or chlorides that may have existed in the feedstock. This final syngas is then piped to the downstream generator, to a hydrogen separator, or a liquid fuel production system. Next slide. So these are examples of various feedstocks that we have successfully processed in the HelioStorm system. Everything from shredded poplar wood and corn stover to pyrolysis oil to simulated MSW to real MSW from the city in California to plastic waste to C&D waste. All of this has successfully been gasified. And we've tested up to 1/2 inch and with moisture levels up to 50%. Next slide, please. Okay, so for many of our test runs, in addition to our inline gas analyzer, we've captured syngas in collection bottles and sent them to Idaho National Laboratory and to Atlantic Analytic Laboratory in New Jersey for analysis. We've also worked with Hazen Labs in Colorado for analysis of the solid materials, including feedstock prior to processing and residue after processing. The results that you see here are from tests that were conducted with our original 2-module R&D unit. That unit was running at less than full power and without any gas composition optimization. This means that even without controlling the oxygen content in the environment to ensure optimal conversion to carbon monoxide rather than CO2 or oxygen, the results tell a pretty consistent story. First, the HelioStorm can gasify just about anything you put into it. Second, it's going to produce syngas composed primarily of carbon monoxide and hydrogen, the first 2 columns. Third, methane and longer chain hydrocarbons are at or below the detectable limit. You see we don't see any in these runs. Again, and we got this in a far from optimal testing environment. So consequently, we expect even better results from our current 3-module, fully powered HelioStorm system that we've designed for the Navy. Next slide. And this is what the inorganic residue looks like that we collect at the bottom. It's basically the silica and the various metals that have come through form into a glass and metal bead-like shapes. They're inert, and they can be easily disposed of. In fact, a lot of people want to know whether or not we're going to get into the jewelry business, but we're really not considering that. Next slide. So this diagram, again, developed based on test results and modeling for the U.S. Navy Small Business Innovation Research Project that we shows our energy and power balances. Our projected balances. The energy balance is for 1 ton of MSW, and with an energy content assumed of 15,900 megajoules, and the corresponding power balance assumes a processing rate of 3.5 tons per day. So you can see that based on this model, the system will generate 300 kilowatts of power. It will, however, consume about 186 kilowatts of electric power, and that's not just the gasifier, that's the shredder, the chillers, and every part of the system, about 186. The remaining 114 kilowatts can be used for power on-site or to be exported to a local grid. Since it takes 6.86 hours to process a ton of feedstock, a very manageable input rate of only about 1.3 ounces per second. The system will generate 114 kilowatt hours per hour, or about 780 kilowatt hours per ton of surplus electricity. Next slide, please. So where have we been? Between 2012 and 15, as I said, we were standing up the company, getting initial investment dollars and exercising our option with INL for the underlying technology. And in 2016, Criari and we were awarded the phase 1 grant of the SBIR process. And that was followed 1 year later with a 2-year SBIR phase 2 grant. Next slide. So where are we today? Well, for starters, this is no longer a science experiment. We have been safely and routinely operating our full-scale R&D unit for intermittent testing and demonstration runs in our facility in Idaho Falls for over a year and a half now. We have successfully processed feedstock ranging from biomass like hybrid poplar and almond shells to MSW to bio-oil and to waste coal with independently verified results as part of the sequence of government-funded projects with INL, NREL, and the U.S. Navy. And we have tested these at moisture levels up to 50%. We are now nearing completion of our second system, a full commercial scale unit that we will use to demonstrate the effectiveness of the technology to the U.S. Navy for the SBIR phase 2 project we are conducting with our engineering partners at Criari. As part of the SBIR project, our team is integrating front and back end components to demonstrate the complete end-to-end solution by the end of this July. The final set of energy balance and reliability testing and demonstration over longer-term runs is the subject of a proposed SBIR phase 3, which we hope to get and begin later this year. At our current pace, if successful, we anticipate being able to begin filling orders in early 2021. And the next slide is the last slide. Thank you for your attention, and I'm happy to try to answer any of your questions. And with that, I'll turn it back to Scott.
Thank you, Dr. Haspel. I do have a few questions that have come in while you were speaking. And so in perhaps simpler terms, what do you mean by parasitic load and how your system compares to the previous ways of gasifying?
Sure. One of the big complaints about plasma gasification is that it consumes more energy than it produces. The amount of energy that it consumes is called the parasitic load. As you can see from our, and that's why they have to be so large, because they have to generate a lot of electricity before they end up actually being able to produce anything that is surplus. In our case, even at small amounts, we are able to generate surplus electricity. So even though we do consume probably 30% of the electricity we generate, we are going to have 70% of it available for use or sale.
Okay, thank you. And a related question is, how are such high temperatures reached without, maybe you just partially answered that in your last response, how are such high temperatures reached without consuming more energy that would exceed the value of the recovered syngas?
Okay, well, that's the beauty of this new technology and the patents that we have. Dr. Kong has found a way to create long arcs so that he can fill an entire cylinder with plasma gas. So we are able to put the waste directly into this environment, this ionic, super hot environment. 5,000 degrees is actually the temperature of the surface of the sun. So we're doing this at temperatures higher than this temperature of the surface of the sun. And the competitors They use a plasma torch, which are very effective. They're primarily used for heating, for cutting, cutting torches. When you go to the movies and you watch the crooks break into the vault in the bank, the torch that they're using to cut through the steel door is probably a plasma torch. Very effective that way. But what our competitors are doing is they're using that very small hot tip to heat air or molten glass. There's a system out there now that basically puts the torch into glass, makes it molten. At the temperature of molten glass is 1700 degrees C. And then they use that as the medium in which they convert waste. But it's only 1700 degrees, and as I pointed out, sort of lots of different things begin to happen when you manage to crest 3000. So that's the basic difference. And I will tell you, I put my hand on the outside of the HelioStorm while it's operating. It's totally cool to the touch. It's 10,000 degrees inside, but totally cool on the outside.
Well, that's you anticipated one of the other questions that we had received was how do you cool the unit? So as you said, it's safe to the touch on the outside. Is there any mechanism within the inside to keep the plasma at that temperature? Is there any sort of cooling suppression, or do you just heat it to where you need it?
No, basically inside of the gasifier is a shell made of graphite, and it's inside of that shell that the temperatures are at 10,000 degrees, anywhere from 2 to 10,000, maybe even a little hotter. Beyond that, there's insulation material, and beyond that is a water-cooled jacket. And so there are a series of ways to reduce the temperature. I mean, the heat will have to escape somehow. We're not violating the laws of physics. And the syngas itself comes out quite hot, about 600–700 degrees C. So there is a lot of heat involved. But the syngas heat you can recover through heat exchangers. We expect in version 4, 5, whatever, that we'll be able to use thermoelectric materials inside the gasifier to capture that and turn it into electricity as well. But the heat is, we're very cognizant of the amount of heat that we're producing, but it's very controlled. As soon as you turn off the electricity to the electrodes that create the plasma arc, the arc is finished, so no more heat is generated. And as I said, there's sufficient insulation as well as cooling going on to such that you can touch the outside of one of the HelioStorms.
Great, thank you. I actually have a couple of questions pertaining to the capacity of the feedstock. So initially, the first commercially available prototype, or I guess production model, I guess you would call it, what sort of feedstock capacity are you targeting for that?
Okay, what you see is our full-scale model. It will do 4 tons a day. To do more tons, think of this as a Tesla battery, or think of it as a server farm. Lots of small computers make up a server farm. Lots of small batteries make up a Tesla battery. Think of an 8-cylinder engine. There are 8 cylinders in that engine. And now there are cars that only use 3 when they need to, but use 8 when they have to. So basically, scaling this to larger involves having multiple HelioStorms. With that said, you can have large shredders. You can have large, you can use gathering systems to bring together the syngas and then put it through larger Fischer-Tropsch types of chemical or fuel production schemes. You can use bigger gensets. If it's hydrogen separation, you can use a bigger separator. There can be economies of scale throughout, but we think that the optimal size for this process, this technology is what we have, primarily because most waste to energy type of systems fail, not so much because of the technology, but because of the difficulties in feeding their beasts. And by keeping it at 1.3 ounces per second, we have a very manageable feeding capacity. And then using gathering to bring the syngas together makes a lot of sense in our view. In addition, if you end up with having an issue with one, rather than having to shut the entire facility down, you only have to shut one cylinder of the facility down. There have been a number of cases in the last few months, actually probably last half year, where there have been fires and or equipment failure at waste energy plants, and they had to move 20, 30 tons, million tons of waste to landfills. Not what we would like to see. We think having a modular approach to waste to fuels, or waste to electricity, or waste to hydrogen is a smart way to go.
Along those lines, to maintain the optimum feed rate for the stock, what is the ideal sizing of the particles going in there?
We believe it's a 1/2 inch. Basically, the need is for the waste particle to remain resident in the HelioStorm long enough to gasify. If they're much bigger, we will not see full gasification, full conversion. The 1/2 inch size seems to be appropriate to obtain full conversion. Okay.
And to round out this section of questions, so in looking to the future for commercializing this application, what I think I heard you say, please correct me if I'm wrong, is that if you wanted to reach something like 400 tons a day or 600 tons per day, you're really just talking about setting up several of the machines in parallel and with controlling the feedstock into multiple reactors. Is that correct?
That would be correct.
Okay. And do you have any idea what it would cost a ton, what it would cost per ton to process MSW through the gasifier as a conservative estimate?
That's a good question. It really depends on, that's interesting. You have to make assumptions about the length of the life of the capital, how much, where it is, because labor costs are different per region and so on. I'd be happy to take that as somebody would like to send me that as a question with some parameters around their specific area. I think putting in it's very misleading to give a number. In a developing country with very low labor costs and high electricity rates, this becomes a very, very economical. In the United States, with very cheap natural gas prices, at least in terms of electricity, it's not, except in very remote locations. If you want to talk about hydrogen, it's about half as costly as using electrolysis. So it really depends on what the end product is, and it's a very good question, very, very hard to answer.
Okay, I do appreciate that answer, and the attendee who asked the question has your email address there on the last slide to contact you with more specifics, like you said. So back to the question about the sizing for the feedstock. Would it be feasible to, let's say that a customer has larger feedstock, let's say due to the grinding machinery and whatever they're pre-processing it. Have you guys done any testing as far as accepting larger feedstock and then having it, either run through reactors in a serial manner, or I guess my question is
Okay.
is there a way to accommodate larger sized feedstock? Should that be appropriate for a customer?
You know, I'd like to talk to the customer. It is, of course, possible. One of the things we can do right now, we're talking about a 3-module gasifier. It may be appropriate that it may only need 4, you know, in order to accommodate a bigger piece, because the residence time would then be appropriate. But that involves more electrodes, more power supplies, and changes the economics. So it's really all about the economics, and it is certainly possible. It may be simply a function of running it through one more shredder. It may be a need to put it through a hydrothermal conversion device first and turn it into a hydrochar and then feed hydrochar in. I don't know. This again is a very specific question. We think it is certainly doable. I will tell you that the size of one of the ThyssenKrupp gasifiers has to be 100 microns. So various gasifiers require different sizes for different purposes, I think certainly something. It's a front end question. How do you feed us? And something we'd be happy to work with a prospective client to figure out.
Okay, and I guess to ask a more general question, so you're designing the system to be modular such that if you need another layer of plasma electrodes, as shown on the screen now, that would be conceivable to do potentially.
You could put 4, 5, 6. You know, we think 3 is more than enough. We think there are cases when you only need 1. Okay, it depends on what you need to do. Okay. If you've got a pyrolysis system and you've got a product gas and you want to use this to polish, may only need 2. If you've got waste from a landfill, probably needs 3. Rubber tires, steel belted tires, all that sort of stuff, probably 3. We won't know until we try it out with the customer and make sure we optimize this for their particular need.
Okay, great. A couple questions about resulting waste. So, do you have any general metrics of what the reduction waste in to waste out might be? Yeah. Basically, this will reduce your volume by 98 to 99%. Probably about reduce it so you're left with maybe 1/6 of the weight. I mean, again, depends on the composition of what you're putting in. If you're pretty much putting in just biomass or food waste and things like that, there's going to be next to nothing left. If it'll be dirt and things like that have come through. If you're putting in black bag garbage and there's metals and things like that, most of the weight is the metals, and the metals will melt. They'll turn into those little round globs and beads, and that's probably that. The weight of the metal will not change. So if you've got a lot of metal, that weight's going to come through. But volumetrically, anything that's carbonaceous is going to turn into a syngas, and so all that volume is gone. Okay, great. So on the subject of syngas, you had mentioned during your presentation that you're already working with your engineering partner to come up with a prototype diesel type engine that would run on syngas. Have you done an analysis to know what the resulting emissions are of the syngas as composed to natural gas or propane or gasoline or diesel or anything like that?
So,
is it
the concept, the concept is to introduce syngas through the air intake. The controllers in the genset are literally only interested in the amount of BTUs coming in. So it will be a combination of the diesel and the syngas. So the more syngas, the more BTUs with the syngas, the less diesel. So that's what the Navy's interested in, backing out diesel. The byproduct of that coming out of the genset is the same thing, CO2 and water vapor. I mean, it's only CO and H2. When it combusts, it's interacting with air, and the oxygen is good. The CO is going to become CO2, and the hydrogen is going to become H2O. So it's the same as you're going to get with methane. It's just a substitute. So you need to look at the specs on your genset. Whatever the genset says it's going to be producing, it'll produce the same thing, whether it's coming from the diesel, the methane, or from syngas.
Great. Okay, well, that is all the questions that have come in to me at this point. If you have anything else you'd like to say, Dr. Haspel, before we get off, you can do so. Otherwise, I'll close it out.
Well, I appreciate the opportunity and the attentiveness. Great questions. Clearly you were listening. That's great. And I'm happy to field whatever other questions you might have. You can use the info, or you can use the same back end and just address it to A Haspel, my first initial A and my last name, at cogentenergysystems.com as well. So either way, I will get it.
All right, thank you, Dr. Haspel. Again, this webinar, like all webinars in this series, has been recorded and will be available via YouTube links on both the National Recycling Coalition and Recycling Market Center's websites. Thank you again for joining us. We hope you will join us for next month's webinar. Please visit the NRC and RMC websites for schedule updates.